Hey, this video is going to be about position versus time graphs and velocity versus time graphs. So there are two situations you're going to have to be able to figure out the graphs for: accelerated motion and unaccelerated motion. So unaccelerated is easier. Let's talk about it first. When the acceleration is 0, you don't have to deal with it. An unaccelerated motion will always look like a straight line on the position versus time graph. It'll look like one of these. So a straight line on a position versus time graph is going to have a straight horizontal line on the velocity versus time graph. Because remember, velocity is the slope of the position versus time graph. So this red thing has a very high slope, but it's only one slope. So this would be the velocity time graph that goes with it. It's a constant, pretty high slope. This blue one has a lower slope than the red one, but it's still positive. So you'll have a constant, pretty high value for the velocity right there. This orange one actually has a negative slope. So you would have a constant negative value for this orange one. And this sky blue one is, well, it has the same slope as this red one, right? It looks like it's about the same rise over run. It looks like it's about the same steepness. Ooh. Okay, so it looks like it's about the same steepness. But this is here to show you that it doesn't matter where the line starts. The velocity versus time graph only cares about the slope. So the velocity versus time graph for this blue one will look like this. Same as the red one, because the slope is the same. It does not matter where you are at. So that's unaccelerated motion, and hopefully it's pretty easy. If you want to go the other way, all you have to do is you have to look at the velocity time graph and say, is this a positive value or a negative value? So is it a positive value up here, or is it a negative value down here? And if the velocity is a negative value, then you have a negative slope, like this. If instead of being here, it was up here in the positive part, then you would have a positive slope, like this. And it would not matter where you started the line, because you can't tell from this. All you can tell is the slope, not the position. So one final thing before I move on to accelerated motion. The acceleration is the slope of the velocity time line, just like the velocity is the slope of the position time line. So this has no slope. It's unaccelerated. That's why all the unaccelerated motions have this kind of line, horizontal. But if you have this instead, now this has a slope, right? It has a rise over run. It is steep. It's not flat. And if this has a slope, then you have an acceleration to deal with. So acceleration can best be thought of as the slope of the velocity versus time graph, right now at least. And I'll tell you how to deal with accelerated motion, not unaccelerated motion. So it's actually easier if I do this with the velocity time graph first, and then I move on to the position time graph. So here are some example motions on a velocity versus time graph. Just so you know, you will not in this class have to deal with curvy velocity time graphs like that. That's not going to happen, so don't worry about it. Straight on the velocity time is as difficult as we're going to get. So the first thing that you will have to do is you will have to be able to tell me if there's a positive or negative acceleration. And that's pretty easy. Like I said, you just look at the slope. If it's slanting up, it's positive. If it's slanting down, it's negative. So this red one is positive acceleration. Orange one's positive acceleration. This teal one is negative, and this blue one is negative. So this red one has a higher positive acceleration than the orange one. These two look like they're about the same. Maybe the teal one has a bigger negative acceleration than this blue one, but whatever. So positive negative acceleration is not that difficult. But what is difficult for people is figuring out if something is speeding up or slowing down. So I'll tell you how you figure that out. This is zero velocity, this line right here. So if you are getting closer to the zero velocity line, you're slowing down. If you're getting farther away, so you're moving up here or you're moving down here, then you're speeding up. So for example, this red line is speeding up because it starts here and it is leaving this zone next to the 0. This orange one, similarly, is leaving the zone next to the 0, so it's speeding up. This blue one is also speeding up because it starts close to the 0, but it ends far away from the 0. This teal one right here is, now this is a tricky thing. For a while, it's slowing down because for a while, it's getting closer to 0 velocity. But after that, it's speeding up. It's getting far away from 0 velocity. So even though the slope didn't change, during the first part here, it is slowing down, and during the second part here, it's speeding up. How can that be? Well, it looks something like this on a position time graph. Right here, it starts with a positive velocity, like this. Then it gets to a 0 velocity, and then slows down like that. Gets to a negative velocity. So whenever something crosses this axis, it stops slowing down and starts speeding up, just like a ball that you throw up in the air. This point right here, where it actually crosses, is this point, where you have 0 velocity. And so that's how you tell. You look at if it's getting farther away or closer to this middle line. I'll give you a couple more examples. Also, I've been saying speeding up. Maybe you don't know. Speeding up means going faster. It doesn't mean actually moving in the upward direction. It just means getting faster. So this red line right here is getting faster because it is getting farther away from this 0 velocity line. But this blue one, even though it has the same slope, this is getting slower because it's getting closer to the 0 line. So if I allowed this blue line to extend, if I allowed it to go further, like this, slower, 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 stopped, faster, 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 it would be getting slower during this section and getting faster during this section right here. So slower, then faster. Whenever you have something like a free fall motion where you throw something up in the air and then it reaches a maximum height and then stops going up and starts falling down, you'll have one of these crossovers. So hopefully you understand what accelerated motion looks like on a velocity time graph and how to tell if it's speeding up or slowing down there. But you need to be able to tell it from a position graph too. So accelerated position versus time graphs are curvy. They can curve in a couple ways, but you only need to look at 2 points to tell me what's happening. You need to look at the beginning and the end. So here is an example of what I mean. This is a curve. Now, I only have to find the slope at 2 places to tell me what's happening. So the slope here at the beginning looks like this line. So that's the slope right here, around this point. And this slope looks pretty positive. But over here at the end, this is looking more like a horizontal line. So this slope right here is 0. So what I know about this, what did I do? So what I know about this line is that it looks like this on the velocity time graph. It starts out positive and it ends up 0. And we know that getting closer to the 0 is slowing down. So this is slowing down, this red line right here, because it starts off with a positive slope and it ends up at the 0 one. Similarly, if I start off with a negative slope and I end up like a 0, it is also slowing down because I start off with a negative slope and it ends up near 0. Now, if I did allow this to play for longer and I kept extending this line, what would happen is it would stop slowing down and it would start speeding up. But I don't normally allow this to happen. I just cut it off right here and I say, is it speeding up or slowing down? And you tell me it's slowing down. So position versus time graphs that are speeding up, they look like this. They start with very low slope and then they end up with high slope, like that. That's speeding up because the slope here between, let's say, these 2 points is much higher than the slope here in between these 2 points at the beginning. So only look at some points at the very beginning and the very end to tell. Finally, you have this, where it's going down like this. This is also speeding up because it starts off with a near 0 slope and it ends up with a very high slope, or a very negative slope. So on the velocity versus time graph, it would look like this. It starts off near 0, then it ends up very negative, and then you connect these, and you see, oh, look, I didn't connect that, that was bad. So then you connect them, and you say, look, it's getting farther away from this. If it's getting farther away from the 0, then it is speeding up. So let me put up a little summary thing here, and hopefully that'll help. So if you have no acceleration, the position versus time graph is going to look like a straight line. If it's a straight line with a positive slope, you have a constant positive velocity. Straight line with a negative slope, constant negative velocity. Then a straight line with no slope means you have 0 velocity everywhere. But if you have acceleration, It's either going to be positive or negative. Positive acceleration is a positive slope on the velocity versus time graph, so this is what positive acceleration might look like. So this is what a positive acceleration would look like. All of these four are positive acceleration because they both have positive velocity time slopes. But this one, these two right here, they're getting faster, and these two are getting slower. Now you know it's getting faster from position time because the slope starts low and then it ends up high. On the velocity time you know because it starts close to 0 and it ends far away. This one down here, you know it's slowing down because the slope starts very negative, ends up at 0. Right here, it's getting closer to that middle line. Negative acceleration looks like this. And these two are examples of negative acceleration that are getting faster, right here, because you can see the slope is near 0, and then it's positive. Down here, because it's getting farther away from the 0 line. But these two are both getting slower, because it starts off with a very negative slope and ends up with near 0. Here, it's because it's getting closer to this line. You cannot tell if it's getting faster or slower just by looking at the sign of the acceleration. You actually have to imagine this velocity time graph and then see if it's getting closer or farther away from the 0. Sorry that was kind of long. Hope it was helpful.